Good morning to all. Today we are going to discuss about case study on CFD. So in that CFD, it is a computational fluid dynamics. It will be applicable for all the numerical simulations. So in that CFD, it will be applicable for gas dynamics and fluid dynamics. So today we are going to discuss about one case study on NASA X-43A aircraft. So in that aircraft, so what are all the techniques they are using for this study? These are all the topics will discussed by students. Now I hand over the sessions to the students.
Today we were discussing about a case study on a project. NASA X. The test vehicle is X-43A. The purpose is to demonstrate the aircraft's body to withstand the hypersonic speed, that is from Mach 7 to Mach 10. Challenge is to design an airframe that withstand the extreme aerodynamic force under thermal loads in the aircraft.
In this research, in X-43, characteristics of aerodynamic load and thermal load above on the aircraft. While flying the aircraft in Mach 7 to 10, the aircraft frame and engines complexity will be very high, and the airframe and the structure of the aircraft will be optimized. We have to optimize about this.
Okay, we have already discussed about the case very well, I think. And then in this case, NASA's X-43 aircraft, we are going to test the workflow by CFD workflow, and then we are going to take the altitude as 100,000 feet, and then we are going to set the speed from Mach number 7 to Mach number 10. First, we are going to build a model of this aircraft in software simulation. So for this purpose, NASA uses softwares like ANSYS and many softwares. So after the generation of the model, we are going to apply the loading conditions and then the end conditions and also the boundary conditions of the aircraft, and also we are going to apply the environment conditions in the airlines also in this. So after applying all these loads and conditions, we are going to discretize the model into several parts. By discretizing that, we are going to use an option called meshing. After meshing the component, the parts will be divided into separate meshes, node points and edges. And then we are going to apply the loads and conditions. After applying that, we are going to do a flow analysis on that. After doing that flow analysis, we can get the results from it. So this is the CFD workflow for this NASA's X-43A aircraft. So by doing these kind of CFD workflow, we can assure the computational fluid dynamics of the aircraft. So for this case, it's enough, I think. Thank you.
Outcomes. First one is shock wave prediction. CFD successfully predicted oblique shock patterns and shocks in front of the vehicles, which were later validated with flight data. The second one is heat flux estimation. Enabled estimation of the thermal loads for thermal protection system design. And the third one is engine airframe integration. CFD analysis optimize the inlet design to ensure proper airflow into the scramjet engine at hypersonic speeds. And the fourth one is flight validations. CFD result were in strong argument with the actual flight data from the 2000 March 10 missions. Thank you.
So as from this research paper, the impact of CFD is that before the usage of CFD, there was many physical tests that we have to undergo for checking an airfoil work and everything. For the checking of airflow through the airfoil,
and for that we have to use, nowadays we are using CFD analysis. So CFD analysis is widely used across various industries to simulate the fluid flow and to transfer the related phenomena. So the applications of the CFD is that in aerospace we are using it for aircraft designing and airfoil designing, and for the fuselage designing also. We are using it for drag and lift calculations, and also for the flow separation usages. And here the purpose is to optimize aircraft performance, so that beforehand we will be using many physical tests, and we have to use a lot of money for time for it. But now using the CFD we can minimize our usage of time, and also we can get a better output. Thank you.